A fast-moving object the size of Manhattan is hurtling towards our solar system, and it will make its closest pass to Earth on December 17th. Comet, asteroid, or something else? A Harvard astrophysicist believes there's a strong likelihood this is a craft of alien origin, and the implications, obviously, would have a profound impact on humanity. It could not be a rock at all. 3I Atlas. Tell me the best reason why you think this object may be extraterrestrial and maybe in alien form. Well, first, its brightness implies that if it represents reflection of sunlight from a solid object, it needs to be 20 kilometers in diameter. That's larger than the island of Manhattan, and this is a giant rock. The previous interstellar objects were hundreds of times smaller. So it just doesn't make sense that the third object from interstellar space will be 100 times bigger than the previous two. And we won't see anything in between. And if you look at the trajectory of this object, indeed, it's perfectly aligned with the plane of the planets around the sun. A fundamental question is, was this designed by intelligence? And the more scientists studied this newly discovered interstellar object, the stranger it seems to become. A mysterious visitor is on its way to Earth, moving closer at 137,000 miles per hour. A comet or an alien ship? Researchers and scientists are left puzzled. NASA's new images of interstellar object 3I Atlas weren't supposed to rewrite the rulebook. But when a quantum AI scoured the data, it flagged oddities even veteran astronomers hadn't noticed. Like a tail that faces the sun where standard physics says this should be impossible. The third interstellar visitor ever spotted, yet its behavior defies everything we thought we understood about comets. The results aren't just bizarre, they're deeply unsettling, with patterns no natural explanation can easily cover. If the world's most advanced AI is unsettled by what it found, shouldn't we be too? What is 3I Atlas? And why has this discovery left even NASA's experts worried? The exceptions are only beginning. Dust streaming toward the sun from an interstellar comet is not supposed to happen, yet. That's exactly what the latest NASA images of 3I Atlas reveal. A plume of particles stretching in the wrong direction, defying the basic rules of comet physics. Normally, sunlight pushes dust and gas away, forming a tail that points directly opposite the sun. That's radiation pressure in action, a force so predictable it's used to steer spacecraft. But here, the dust clings to the sunward side, as if gravity and light are playing by a different set of rules. Spectroscopic scans add another layer to the puzzle. Astronomers look for telltale signs, specific fingerprints in the light spectrum that reveal what a comet is made of. In almost every active comet, you'll find diatomic carbon, cyanogen, and clear markers of other volatile gases glowing at precise wavelengths. These are the chemical traces of a comet's awakening as sunlight hits its icy core. But in the first weeks after discovery, 3I Atlas showed none of these. No cyanogen, no diatomic carbon, not even faint traces. The spectrum was nearly empty where it ought to have lit up. Think of it like watching a campfire that burns hot but doesn't make any smoke. The dust is there, obvious, even dramatic in the images, but the usual chemical evidence is missing. It's as if the comet is venting material in a way no one anticipated or expected from a composition that doesn't match anything seen in the solar system. Only months later, as the comet closed in on the sun, did a faint whiff of cyanogen finally appear late, still sluggish, and out of step with the dust activity. This combination dust streaming sunward. A coma without its usual gas, and a delayed chemical responses left researchers searching for answers. A few point to a possible surface crust, hardened by billions of years in interstellar space, shielding inner ices from the sun's heat. Others wonder if the comet's spin axis is locked in just the right way to expose only specific regions. But the basic contradiction remains: a sun-facing tail, absent volatiles, and a profile that fits neither comet nor asteroid. The physics just doesn't add up right now. NASA's imaging teams faced a challenge unlike anything else. Calibrating the stacked exposures from the Atlas survey, they traced the faint 3I-ATLA's frame, moving points by frame. Each pixel carried the slash arc. Each pixel carried the weight of the cosmic background. The resulting data pointed to a nucleus no smaller than 0.3 kilometers and possibly as large as 5.6 kilometers across. That's not just big for a visitor from another galaxy. It's enormous. For background, ʻOumuamua, the first known interstellar object, was likely less than 200 meters long. 2I Borisov, I estimated, was a kilometer. 3-1 Atlas could be 5 times that or more. Only 3 confirmed interstellar objects have ever been recorded. To locate one of this size, this active, and this close is statistically staggering. The odds of randomly detecting such a giant, given the survey's sensitivity and the volume of space it covers, are vanishingly small. Most interstellar objects slip by, hidden in the glare of faraway stars or too faint for even the largest telescopes. Yet here, the data chain is clear. From the initial Atlas discovery to follow-up with JWST and Hubble, the same vastness is confirmed in each image's active core. The brightness of the object, measured across multiple nights and instruments, rules out small debris or a swarm of fragments. This is a single, monolithic body, an ancient traveler forged in a different star's disk. Astronomers tried to model how such an enormous interstellar object could cross our path. Simulations suggest the odds are less than 1 in a million for a random ejection from another system to land one so close to Earth's orbit. The scale alone raises concerns about what else might be lurking in the dark, undetected. This is not just another comet. It's a statistical outlier, a cosmic heavyweight that defies the usual odds. The numbers demand attention. But the real shock comes from where it's going next, a trajectory that brings it alarmingly close to several major planets, one following the other. Trajectory calculators at NASA and JPL started with a simple question: where exactly is 3I Atlas heading? The answer? It turns out, traces a path through the inner solar system that's anything but ordinary. On October 3, 2025, the comet will pass within 0.19 astronomical units of Mars, just 28 million kilometers. That's close enough for even the most conservative models to flag it as a close call, especially for an object hurtling in from interstellar space. Only 4 weeks later, Atlas swings past the Sun at perihelion, reaching its maximum speed of 68 kilometers per second. Then, on November 3rd, it comes within 0.65 astronomical units of Venus. That's inside the orbit of Earth. For context, a region rarely crossed by any known comet, let alone one from outside the solar system. Each leg of this journey is mapped in fine detail. Timestamps, distances, velocities, and the precise angles between the comet's track and the orbits of the planets. The numbers are clear, but the pattern they form is anything but expected. It's a route that seems calculated, almost purposeful, as if the object is threading a cosmic needle between the inner planets. Gravitational assist basics explain how a planet's motion can speed up or redirect a moving object. The effect is subtle, for 3I Atlas, but measurable. The path taken by the comet bends as it passes each planet, but the overall path remains hyperbolic. It's an open curve that will eventually fling it back into interstellar space. What sets it apart isn't the physics, but the sequence. Mars first, then Venus, each within a narrow window of time and space. Calculating these encounters requires a precise understanding of the planet's positions, the comet's speed, and the Sun's gravitational pull, all of which have been confirmed by independent teams using NASA's Horizon system and JPL's DE-441 planetary ephemeris. The path through the inner solar system is now set. Each close approach is locked in by the laws. of motion and gravity. Yet, the odds of this specific sequence occurring by random chance remain an open question. What's certain is that the journey of 3I ATLAs is unlike anything astronomers have tracked before. The raw data points 58 kilometers per second, October 2025, November. Distances measured in tens of millions of kilometers conjure up an image of a visitor following a route that defies easy explanation. And as the comet races toward its next target planet, the stage is set for a deeper look at just how improbable this trajectory really is. Probability in astronomy is rarely this unforgiving. When Adam Hibbert and Abraham Lowe ran the numbers on the path of 3I ATLAS, even expert dynamicists were shocked by the outcomes. Monte Carlo simulations, essentially billions of random trials, were used to estimate how often an interstellar object entering the solar system with similar speed and inclination would pass as close to Mars, Venus, and Jupiter as 3I Atlas is now set to do. This isn't just a matter of chance alignment. Each planet occupies just a small portion of its orbit at any given time. For a hyperbolic visitor to pass within 0.19 astronomical units of Mars, then 0.65 astronomical units of Venus, and finally skim Jupiter's orbit all within a few months, requires a sequence of timing and geometry that borders on the impossible. The simulations treated the entry time as a free variable, holding the direction and speed of the object fixed and allowing the planets to move around their orbits. Most scenarios missed by tens or hundreds of millions of kilometers. Only a rare handful matched the observed sequence. The analogy that Lowe uses is striking. Imagine tossing a dart at a spinning globe and hitting 3 tiny cities in a series, blindfolded, with the globe circling around each throw. The odds don't just stack, they multiply, shrinking with every required planetary meeting. The raw output of the Monte Carlo study is a sea of near misses, with the actual path of 3I Atlas standing out as a red dot in an otherwise empty patch of statistical space. Some researchers argue that, with enough interstellar objects, even million-to-one events will eventually happen. However, this sample size is 3, and only 3I Atlas cuts this particular path. Quantum AI systems are built to spot what the human eye misses when they go through the entire stack of endless survey images for 3I Atlas. The first flag wasn't a shape or a color. It was a rhythm. The AI's period detection algorithms, running thousands of parallel checks, locked onto a repeating cycle in the comet's brightness. Not a random flicker, not the slow fade of a comet drifting from the sun, but a tight, persistent periodicity. Every pulse showed up right on schedule, like a heartbeat buried in the noise. Statistically, every p-value threshold set by the researchers was passed by the signal. The odds of this pattern appearing by chance in such a turbulent, dusty environment decreased to less than 1 in 10,000. Traditional analysis would have struggled here. Human astronomers might scan dozens of light curves in a night, looking for obvious dips or rises. The AI, by contrast, processed all available photometric data at once across filters, nights, and telescopes, testing every plausible period from minutes to days. It's the computer's version of listening to 100 orchestras at once and picking out a single violin's repeating note. This type of analogy processing is where quantum-inspired systems shine. They can sift through mountains of unprocessed data that isolate subtle, consistent changes that would blur together in a manual review. The periodicity wasn't tied to known comet behaviors. It didn't match the expected spin rate for a nucleus this size, nor did it line up with any known orbital resonance. The AI flagged it as a genuine anomaly, something real in the data, not an artifact of the instruments or a trick of background stars. Cross-checks using distinct data sets, including Hubble and ground-based photometry, confirmed the same pattern. The signal was there night after night, persisting even as the comet's overall brightness changed with its distance from the sun. Some researchers liken this to finding a metronome ticking inside a storm, the AI's ability to pull order from chaos. To recognize a hidden clockwork in the glare and dust gives astronomers a new edge. It's not just about seeing more, it's about seeing differently. With this kind of pattern in hand, the next step is clear. Test whether the periodicity ties to a physical property, a structural feature, or something even stranger. But as the anomaly surfaced, another algorithm kept crashing. One that pointed to a force acting on Three-Eyed Atlas that's standard. Models couldn't explain. Acceleration data from the Atlas survey brought an unexpected twist. When researchers mapped the position of Three-Eyed Atlas over weeks, the numbers didn't quite line up with what gravity alone would predict. The comet's path showed a persistent, measurable deviation, tiny but unmistakable. The estimated acceleration was on the order of 10 to 7 meters per second squared, much higher than anticipated from radiation pressure alone for an object of this size. At these velocities and distances, sunlight ought to produce a predictable effect, pushing dust and gas away in a steady outward drift. Yet, the observed acceleration pointed slightly off that axis, appearing as if the comet was being pushed sideways by an invisible hand. The initial proposal for an explanation was outgassing. When the sun heats a comet's surface, jets of vaporized ice can act like miniature thrusters controlling the core. This process has explained similar anomalies in past comet trajectories, such as the well-known case of ʻOumuamua. But here's the catch. The usual signatures of outgassing spikes in cyanogen or diatomic carbon, sudden brightening, or jets visible in high-resolution images were missing or appeared too late to account for the early acceleration. The force was present prior to any obvious indication of active jets. This left two camps. Some scientists argued for a crust of hardened material, perhaps baked solid in interstellar space over billions of years, which could mask or delay normal outgassing. Others looked at more exotic theories. One proposal still hotly debated is that radiation pressure from sunlight could be stronger than expected if the nucleus is unusually thin or reflective, almost like a natural light sail. If that's the case, the physics of this object would be unlike any comet seen before. A possible interpretation recently discussed in workshops is that a combination of faint outgassing and radiation pressure might be at work, modulated by the comet's spin and surface properties. But so far, no single model fits all the data. The force anomaly was flagged by quantum AI as a genuine outlier, not a statistical fluke. The result? A growing list of unanswered questions and a debate that reaches well beyond the usual boundaries of comet research. With each new frame, the mystery deepens, and the search for clarification goes one step further into uncharted territory. Standard. Comet science offers a checklist of possible explanations for the Three-Eyed Atlas anomalies. Gassing jets of vaporized ice acting like tiny thrusters have long explained minute deviations in comet paths. When sunlight heats a comet's surface, ices melt and escape through cracks, sometimes pushing the nucleus in unpredictable directions. For most comets, these jets leave clear chemical traces, spikes of cyanogen or diatomic carbon, brightening events, or even visible images with high-resolution jets. If Three-Eyed Atlas followed this script, the delayed gas signatures and odd acceleration might fit a pattern seen before. Shape is another variable. A nucleus that is long or lumpy can tumble, exposing different areas to sunlight and causing uneven heating. This could cause sporadic outgassing, resulting in the comet zigging and zagging on its way toward the sun. Some researchers point to ʻOumuamua, where non-gravitational acceleration was linked to outgassing, even though the gas itself was never detected. Instrumentation artifacts also merit scrutiny, stacking exposures, removing the background. And errors in calibration can mimic subtle periodicities or apparent accelerations. Astronomers routinely cross-check discoveries using independent telescopes. and data pipelines to rule out such technical ghosts. Each of these conventional explanations is being tested against the data. Outgassing models have been run with various shapes and spin rates of the nucleus. Photometric artifacts are checked by comparing results across multiple instruments and observing teams. So far, none of these ordinary mechanisms fully account for the delayed sunward dust chemistry or the measured acceleration. The mystery remains open, but not for lack of utilizing conventional strategies. A few visionaries have started to ask, what if Three-Eyed Atlas isn't just a cosmic fluke, but a sign of something weirder still lurking beneath the surface? Some researchers, inspired by the sunward dust and the faint off-axis acceleration, have floated the idea that the nucleus could be shaped less like a snowball and more like a fine sheet, perhaps a natural analog of a solar sail. In this scenario, radiation pressure would act more efficiently, nudging the object in ways that mimic artificial propulsion. It's a stretch, but the numbers for acceleration line up with what a reflective, ultra-thin fragment might experience. Others point to the possibility of exotic isosubstances that rarely make it to the inner solar system, like nitrogen or carbon monoxide buried beneath a crust hardened by eons of cosmic radiation. If these ices vaporize only at certain temperatures or under particular solar angles, the outcome could be jets firing unpredictably, causing the strange acceleration and delayed chemistry seen so far. In this view, Three-Eyed Atlas might be a relic from a planet-forming disk radically different from our own. And then there's the debris field idea. One or two theorists have questioned whether Three-Eyed Atlas isn't a single comet, but a fragment from a much larger body shattered long ago and now drifting as part of an invisible interstellar flotilla. If that's true, Three-Eyed Atlas could be the tip of an iceberg, one shard among many, each carrying clues about its lost parent world. None of these ideas can be proven yet, but each one pulls the mystery further from the ordinary and closer to the edge of what we believe is feasible. On July 1, 2025, NASA's Atlas survey confirmed the third known interstellar object, Three-Eyed Atlas, with up to 5 nuclei in its nucleus. Quantum AI tools flagged hidden periodic signals in Three-Eyed Atlas's light curve and detected an unexplained acceleration. Standard explanations like outgassing or odd shapes fail to account for all the evidence. Some researchers have proposed more exotic ideas, but none fit the data fully. Key files, including raw AI outputs and spectral models, remain restricted or unpublished. Scientists agree the anomalies of Three-Eyed Atlas challenge basic assumptions about visitors from other stars and solar system physics. As new data becomes public, the mystery stands. For now, Three-Eyed Atlas forces us to reconsider our knowledge of objects entering from deep space and reminds us that our universe still keeps its secrets.